but I can do
in your
that.
homes, in your kitchen, you have an appliance.
Oven.
That's one. Oh, okay. Follow his lead. His appliance has a door on it. What else has a door on it?
Fridge.
Okay, why is that door there?
So it's the
No,
cold air.
not at all. That's not why we have a kitchen, a refrigerator with a door on it. We need the door to put what on? Magnets. That's why it's there. It's magnets. What? Schedules, artwork, reminders.
Syllabus.
I doubt if I've ever had a student syllabus on the refrigerator door. All right, so today we're going to talk about magnetism. Here's your definition. It's the ability of certain metallic ores, as in O-R-E-S, such as lodestone. I'll spell that for you, L-O-D-E-S-T-O-N-E. To attract pieces of iron. Now, you've all played with magnets, right? At one point or another, you play with a magnet. Sometimes when you bring them together, they'll do this, right? Sometimes when you do it, they'll do what?
This.
They'll repel, won't they? Okay. What you're feeling there is something called, anybody want to put a name on it? Magnetic lines of flux. I mean, can you feel them? Especially when they're repelling, right? So there's classifications of magnets. A natural magnet is one of them. And that is something, and I already gave that to you, that is something called lodestone. And that is a natural material that is found in the ground, and it's magnetized by the Earth's magnetic field. The other type, that was a natural magnet. There's another type called artificial permanent magnet. Which consists of hard steel usually shaped as a horseshoe, which has been artificially magnetized.
All Okay.
Okay. Alnico is an alloy. Yeah, that'd be a pretty good name for a pet, wouldn't it? Hmm? Now, this alloy is made of three materials. Let me give a hint here. I'll break this word down.
Aluminum, nickel, and cobalt.
Steve, did you walk in here today knowing that? Or did you just figure that out?
No, I just assumed.
Your
alloy
capitalization
metals.
for helps.
You did it right when you were here, not, it's not back here. All right, Alnico, yes, and you are correct. That's what it is, aluminum, nickel, and cobalt.
Very creative name they came up with.
And the reason we're talking about this today is this is the prelim for something called an electromagnet. Where we take something like that on the board, look up here. We take something like this, we wrap wire around it, we put current through it, and we call that a what? Electromagnet. Okay? We bring in the concept of electricity combined with magnetism. That's coming. This is just a prelude. All right, let's look at a few laws of magnetism. Every magnet has two poles. A north and a south pole. Magnetic lines of flux, you know, that sensation you get when you feel or play with magnets. These magnetic lines of flux, they go from north to south. Okay, still on the laws of magnetism. We talked about this phenomenon, studying other things. Like magnetic poles repel each other. Unlike poles attract. All right, let's talk about the nature of magnetism. So if we straighten this out, this horseshoe, we straightened it out, we have a bar. Okay, let's say I held that bar here and I dropped it on the floor and it broke in half. What happens in terms of magnetism? I made that a bar and dropped it, and we've got two of them there. What do I have?
Well, you said every magnet has to have two poles, so if
Mhm.
the pole, if it's separated, then is it no longer a magnet?
It still is. This is
Still a magnet.
what you get. You get two. If we drop them again, what happens? The same thing occurs. It maintains its magnetic characteristic. Now, here's another piece on the nature of magnetism. And this is a scenario. If a piece of steel is heated or hammered, while it lies near a magnet, some people aren't going to need it. It's hammered while it lies near a magnet, that piece of steel can become a magnet. Has anybody wondered what is happening? Anybody wonder what is happening to make a material have magnetism from the atomic level? And when I say atomic level, what should you think? The atom. Nucleus, electrons in orbits. Those electrons in those orbits, they're spinning. That's where it comes from. The magnetic phenomena comes from the spinning electrons in their shell. That is referred to as spin magnetic, a spin magnetic moment. So something that is magnetized, it means this. They're all spinning in one direction. Magnetized substances, they spin in one direction. Non-magnetized substances, have we done this yet? They spin this way, and then you can have electrons that spin the other way. Have we done this yet? Can you do that? Can you do that? Okay. But that's what a piece of non-magnetized material is. They spin in opposite directions, yeah. Unless you're ambidextrous, probably. All right, I started to draw up here. I'm going to add to it. All right, these are called magnetic lines of flux here. the more concentrated these lines of flux are, the stronger the magnet. That is called flux density, and you'll need to know that for the exam. Flux density.
Can you repeat what you said before that though? About magnetic lines of flux?
Okay. The more magnetic lines of flux we have, the stronger the magnetic field. That's called flux density. Let's take some examples where you have magnets with varying flux density. In other words, varying strength. For instance, give me some examples of a material that has low flux density, not as many lines of flux.
I can't really think of a specific example of a material of a weaker magnet, but I mean a regular fridge magnet is weaker than
Okay,
a powerful
right,
UV
no.
magnet would be.
Okay. This is a funny subject. So was anybody here ever in the Scouts? I'm not. You were in the Scouts? Right? Did you have something when you went out in the forest? You didn't go out in the field? Okay. What'd you have? Yeah. What's that? That's a magnet. The lines of flux really aren't that great. It just needs to know what? Which way is north? Compared to and I'll give you this scenario. This magnet I'm going to describe has some pretty intense lines of flux. It has a lot of lines of flux. You might be driving by a junkyard someday. You got the picture? Where you what to cars?
Compact them.
They compact them. How do they get that car in there? They have a big old crane, and on the boom of that crane on the tip, what is there? And what does it do?
Pick them up.
It picks them up and drops them in the compact.
How do they change it? How do they turn it off and on like that?
Okay,
Electric flux.
yeah, that would be an electromagnet. So in other words, it's a metal that can be magnetized. They wrap it in wire. They turn on that electricity, which you will see down the road, intensify the magnetic lines of flux. All right?
So it's only
Strong
magnetic when
enough
that
to
current
pick it
is
up.
there?
Pardon me?
So it's only magnetic when that current is on?
Yes, yes. You know, and we'll talk about that. I mean, it's the same thing. You guys have been working with electromagnet. No, I kind of got off track, I'm ahead of myself, but as long as we're on it. Electromagnetic, where have you used something that's called an electromagnet? In your life. You've used it. All right, I'll give you an example. If you go to visit a friend who lives in an apartment or condo, okay, and you go to pull that front door open, it won't open. Why? Because it's locked, right? What do you have to do? Call them. And what do? What do they say to you on the loudspeaker? What have you ever said to anybody on the loudspeaker if you've ever lived in that somewhere? I will buzz you in. Okay? And when they buzz you in, you might hear it. It triggers an electromagnet to do what? release the lock, and you go in. Another scenario, and you may find this when you get into clinical, your tables, your treatment tables. You might want to move your patient around, and you might have to have a foot switch to free up an electromagnet and let the table what? Move around. Take your foot off, it stops. It's not moving. What's that? That's an electromagnet, okay? But we'll get there, all right. All right. Flux density. The greater the flux density, the stronger your magnet. Okay, so draw a little more here. There's two magnets back to back. That thing I just drew on the board, is that going to attract or repel?
Attract,
Why? How do you know?
because you have the opposite poles lined up.
There you do. Very good. Is this what you mean?
Yes,
So if we reverse it, what are we going to get?
they'll repel.
Repulsion. Very good. Good observation. All right. We're going to talk about two more characteristics of magnetic permeability and magnetic retentivity. All right, permeability is the following. The ease with which a given material can be magnetized. So, you know, if I had a magnet, and we had a bunch of these sitting there, would the magnet pick them up? It would. Yeah, it would, if you've ever just sat and played around. I mean, they have created paperclip holders out of what? Magnets, so you've seen it. Good. So that's permeability. The other word is retentivity. The ability of a magnet to resist being demagnetized. All right. So, moving along, we're gonna talk about magnetic classifications of material. In other words, we're going to talk about, you've got a large magnet. What do you think I might be talking about here when I say a large magnet?
You referring to the size of it or the power of it?
Well, they're pretty much the same. Where in the healthcare field do we have large magnets? An MRI, okay? An MRI. Did you ever wonder about that magnet in that MRI room needs maintenance? You're just gonna walk in there with one of those, you've seen them. How would I describe it? That tool chest that's red with the drawers, you've seen them probably. You're just gonna walk in there with that? No, you're not walking in there. You ever wonder about that? How do we do service on an MRI? All right, now, you can, and here's the term we use, ramp it down, or do what? Kind of turn it off. That takes care of the electromagnetic piece. But guess what's still in there? There's no magnet. So you have to have tools that are non-magnetic. Not attracted by any magnetic force. They're not susceptible to being induced by a magnet. So they have to have tools that are what we refer to, and put this word down, non-ferrous. In other words, they can't be magnetized. Certain metals are this way, so we need non-ferrous tools.
Non-ferrous, can you spell that?
Yes, Nonferrous. OUS. And then we have something called ferromagnetic materials. And they are what?
Highly magnetic.
Strongly attracted to the magnet.
And what is that called? Ferro?
Ferromagnetic materials. I had a family member that was going to have an MRI, and this was many years ago, and my wife went in to get an MRI, and I said to the operator, hey, would you care if I just sat in there with her? And they said, yeah, you can do that. I thought, oh, my credit cards are removed, you know, I don't have any metal on me. I'm just going to go in there and sit, you know, maybe talk. They said, yeah, you can do that. Well, guess what I had in my pocket? And it just shot right out, okay? Another story, several of us were standing next to an MRI. It wasn't on, we weren't imaging. And he said, you want to see how I determine if there's a magnetic field here? My friend said, yeah. I said, yeah. He said, so the password, a key, just a key. And I'm holding it, and guess what? It's moving around. Okay. And then the big story is, when they build an MRI room, and they put the machine in, you have to have it certified for fire safety. You know, when you have, and these fire folks come along with their big floor-mounted fans, right to the mag. Okay, so believe it, it's magnetic, and things are ferromagnetic. Okay. And then there's a classification of material called paramagnetic material. This, here's how they describe paramagnetic material. Something that is feebly attracted by a magnet. In my notes, I have an example of that. And that is platinum. It's considered a feebly or paramagnetic material. Now, where does that come into play? You've got to get into this too, in terms of MRIs and magnetism. In other words, you know, it's a matter of taking your credit cards and all that out of your pocket, making sure you have no metal. But are some prosthetic joint replacements made out of a platinum type material? That all has to be factored. Another thing, we noticed that when we started doing MRIs, you had to screen your patients. And here's the road I'm going down. One of the screening questions was, have you ever worked in a machine shop or around an area where they had iron filings? Have you heard this scenario? Why? It's the eye. You could get a shard in your eye and not know it. You go into an MRI, and what's that going to do? It's going to move around, and what could it do? It could do some damage. So they would screen people, and there was a way, and part of the screening was, after the questionnaire, they might send you to go get what we call in radiology orbit x-rays, just some images of around the eye. And if you have a shard of metal in there, you'll see it. Okay. And there's a type of metal classification called diamagnetic. Which actually is repelled by a magnet. Just a couple of examples of material that is diamagnetic. Beryllium, you want me to spell that? B-E-R-Y. L-L-I-U-M. And another material that is diamagnetic is bismuth, B-I-S-M-U-T-H. All right, so we looked at the classifications of magnetic matter. All right, let's talk a little bit about electromagnetism. All right, you all know the definition to this word phenomena? What is a phenomena?
An unexplained experience?
Something that happens and we can't explain why. Okay, electromagnetism is the magnetic phenomena associated with electric currents. So you just look at that definition, we talked about, magnetism and electricity. So we're combining. Okay, you need to understand, and so let's kind of build on this. Understand this. There is a magnetic field always around a conductor in which current is flowing. Now, we have two types of current, don't we?
Direct, no.
Does it matter? Doesn't matter. As long as there's current flowing through that wire, there is a magnetic field, those magnetic lines of flux I drew up there, around the wire. Only when the current's flowing. So you see that little example I gave you about buzzing somebody in? Okay? You're talking about current on, current off, and the strength of a magnet to do what? Keep that door locked. All right, we're going to do some labeling here of some structures. That little coil I drew up there is called a what? Anybody? What you've heard? That's called a helix. Helix. So let me build on this. So now I put a power source in. We have current flowing through the helix. Now this term, I'm sure you've heard. Now this is called a, anybody ever heard of that? You put current through a coil of wire, it's called a solenoid. Ever heard of that? I think if you ever studied the electrical circuit in your car, the word solenoid would come up. I think it has something to do with the ignition switch. I'm no mechanic. So now, you know, we started with a helix, we went to a solenoid, and now I'm going to take and through these loops here of the helix, I'm going to put now what do we have? What's that called? You put, what did I put through? What did I, you see where I drew a bar? What?
Filament?
Filament's good, yeah, but not right now. I just kind of drew a soft iron bar down through the loops. What's that called? That's an electromagnet. When you add, and we're going to call it a soft iron core. That's called an electromagnet.
What was the bar called again? Sorry?
A soft iron core.
Soft iron core.
Put it down through there.
Thank you.
And when you put current through that, you have a very strong magnetic field. Remember now, you only have the magnetic field when current is flowing. Anybody have any questions?
When you added the
Bar?
bar, you added more coils? Are those?
Well, I just did it for effect.
Okay.
Yeah, it's for effect. Well, you will see down the road too, yeah. More coils and less coils do matter. We'll get there.
Okay.
Any questions? All right, so let's talk about something called electromagnetic induction. So, I'm going to come back to this. See the magnet? You see the magnetic lines of flux? Let's say, for instance, this is a wire. And in the wire, we just move the wire. Where it cuts across these magnetic lines of flux, what do you think starts to happen in the wire? Pardon me? Okay. The wire, for some reason, okay, we'll get to how the wire moves. The wire moves. And it's cutting those magnetic lines of flux. What happens in the wire? Okay, yeah, you're thinking it. There you go. Okay.
The wire becomes magnetic?
Yeah. Okay. Okay. So let me draw something. Did you say you live in McClenny? Oh, yeah. Anybody else? Okay, that's not. All right, Steve, it's coming your way now. I'm going to draw something. When you guys can tell what I drew, everybody wants to live in the country. Huh? What am I drawing?
A windmill?
Yeah, a windmill. When you drive home. All right, so the wind moves the blades. What's down here? What's down in that box at the foot of the windmill?
Something to gather all the energy.
A magnet, right? What's the windmill moving? The wind is moving the blades, but in here, what's in here that's moving? Because the wind, the thing is turning. What did I just say? What did I do when I did?
A wire.
A what?
A wire.
A wire is moving across the what? The flux, giving the farmer what? Lights. When the wind doesn't blow, guess what the farmer doesn't have? Lights. That was the whole concept of how a windmill works. There's a wire in that box cutting across magnetic lines of flux. It just sits there, the magnet. And when the windmill thing, when the turbine starts, you get electricity. Okay? But, do you see them that much more today? Actually, you're probably seeing more of that in pictures. Some artists drawn on
They were all over California when I drove through California. There was one area, I
wind
don't,
power.
yeah, I don't remember where it was, but there was tons.
I'm not surprised. But since World War II, there's been legislation that has pretty much caught up to it called rural electrification, which means what? They put in electricity through power lines or underground to whom?
People out in the middle of nowhere.
Farmers, yeah. Okay, so they've electrified America rurally now, so that the concept of a windmill really isn't plain. Pardon me?
Have you ever been to Long Island?
Me?
Yeah.
No, but I've been to where where is it? Flushing Meadows, where they do the US Open tennis, and the Mets Park is there. I think that's on the way to Long Island. Why? That's close.
So I was asking if you wanted to see if you thought that was country, but
If what?
if you thought that that was like, looked country to you.
I think there's some country out there, and I think it's really treasured.
It's like a different type of country, it's like winery fields.
Yeah, okay, yeah.
Instead of like farm, there's some
Yeah.
farm fields, like
Mhm.
there's like pumpkin fields and
Oh, yeah.
seasonal fields, like
Sure.
strawberry and
So
summer.
farmers markets must be.
Yeah, it is, and that's where I grew up, but I never considered that country.
Okay. Did you
until
have
I moved
pastures
here.
with cows and steers, and did they milk?
Did you have to pick snap peas?
Some,
Buy a gallon bucket?
there's some, yeah.
Sure, I'm sure, but as time goes on, those fields are what? Developed, right? Yeah.
I never thought I was in the country until I moved, and then went back, I was like, wow, this is crazy. Chickens everywhere, guinea hens, I was like, you're on the road, dude.
All right, that's so we're going to leave off for today. We're going to pick up this discussion next week. We'll finish up this chapter.
Did you have an official definition for electromagnetic induction, just so I can make sure I have it written down accurately?
I just wrote down the wire.
Well, it's simply this, putting a current in a wire.
Okay.
Yeah, we're inducing current. So that's how a windmill works. All right, so I'm going to give you this time. It's release time to go and work on your projects, which is creeping up, you guys.
I was thinking, I was like, oh God, they're ready to finish, like, I need to sit down before like February something, and I was like, oh my God. I did all this work, and it's due on March.
But you're ahead of the game. Okay, it should give you a level of comfort.
It does.